not there? Okay. I'm working on articulated arm calibration of the double show experiment, and I'll go into what all of those things mean in the meat of the talk. So what is double show? Double show is an attempt to try and explain why the universe has stuff in it. So by default, you would assume that the universe would be made up of a uniform field of radiation, which is not particularly interesting. But there are things in the universe that are not radiation, and therefore there needs to be a reason why. So how do we do this? We are looking at subatomic particles that are generated by nuclear reactors. So these subatomic particles are, in particular, being generated by a pair of nuclear reactors in the French-Belgian border at a community called Chooz, C-H-O-O-Z. There was a previous experiment that took place here called Chooz, and this is an expansion of that experiment. It expands by adding a second detector so that you can do comparative analysis in terms of distance, because you expect these particles to fall off. So what do our detectors look like? They're like matryoshka dolls, those Russian nesting dolls. In the center, you've got a sensitive region, and then you surround it with volumes to try and filter out noise and be able to identify uniquely and clearly the particles that you want. So the particular particles that we're looking at are neutrinos. You may have heard of neutrinos before. They are small subatomic particles that weakly interact. By weakly interact, that means they don't interact electromagnetically. They don't interact with the strong nuclear force, which is sort of what holds protons and things together. So they pass through ordinary matter enormously. You need over a light year of lead to stop a neutrino, assuming that it's just flying along. So in the standard model of particle physics, you can see the three families of neutrinos referred to as the electron, muon, and tau neutrino. These neutrinos are generated by a number of different sources, most notably nuclear reactors, as we're looking at there, and the sun. Initially, in studies of neutrinos, Ray Davis, no, not the one from the Kings. This Ray Davis looked at neutrinos coming from the sun, and he measured there was a neutrino deficit. That is, we expect to see so many neutrinos because the sun shines so brightly, and we have a very reasonably good understanding of how the sun works. But we didn't see enough, so there were a lot of speculations as to what could possibly be causing this. Some more believable than others. The neutrino burglar was not a well-received hypothesis. And it turned out that what later experiments confirmed that what's happening is these neutrinos are changing type. So that you can produce one type of neutrino from, say, the sun or a nuclear reactor, and then as it flies along, it has a chance of changing into one of the other types of neutrino. This means that if you try and measure, if you are looking for one specific type, as previous experiments did, you will measure a deficit. And what we are trying to do with our experiment is we're trying to exactly measure how many neutrinos go from this type to this type. We're doing this by measuring the neutrinos that are generated at one location and then at a second location. If you take the difference between the number of neutrinos from position 1 to position 2, you will see the deficit that's caused by this interaction. So, how do we do this? An important part of being able to measure these particles, because we don't see a lot of them, we see maybe 40 per day out of millions that are being generated by the nuclear reactor because they weakly interact, is calibrating our systems to make sure that we completely understand every single signal that goes on. When you only have 40 events per day, you have to be really careful to be able to reject noise. So, traditionally, this is a neutrino signal. So you've got a neutrino coming in, it interacts with a proton inside of the detector to produce a positron or an anti-electron, which is captured instantaneously and produces a light flash. And then secondly, a neutron is also generated by this event. And this neutron will move through the detector thermalizing, and then once it thermalizes, it will capture on a gadolinium nucleus inside of our sensitive region and produce another light flash. So you're looking for this unique double signal. So this is great, but you'll notice that we're measuring light that's coming off of signals. We're not directly measuring neutrinos. And we use the light as a proxy for neutrinos. The more light, the more energy. But the challenge is trying to match the amount of light that you see to the amount of energy that was caused by the incident particle. So, again, this is our detector. When you're trying to calibrate something like this, because of this multi-layered structure, you can only come in through the chimney. You can only come in through this top area here, and this width of that structure is approximately 10 centimeters wide. So if you're trying to introduce sources into this detector, you have a lot of constraints. So traditionally, calibration has been done along the z-axis using a z-axis calibration or a fish line system, which is basically a radioactive source of known energy and intensity that is lowered via a string, effectively, into the detector, and that just hits along the z-axis of the detector, and that's great. And that allows us to get a good idea of the mapping between particle energy and amount of light seen. The challenge is about everywhere else, because this detector, being a cylinder, is not spatially uniform. And so because it's not spatially uniform, for example, the corners will look very different than the center of the detector. If you want to be able to build a true detector map that matches particle energy to light seen, you need a better tool. We build this better tool. This is the articulated arm. So what it does is it goes down into the detector and it bends, and it has a radioactive source at the tip. So this seems relatively straightforward, like it shouldn't be a big deal, but there's a lot of constraints on what you have to be able to do with this articulated arm. To begin with, you have material compatibility requirements. So the center of our detector is this gadolinium-loaded liquid scintillator. This stuff is very sensitive. Previous experiments have been ruined by introducing materials into their sensitive regions that interacted over a long period of time to produce degradation in the scintillator. So we're limited to only using stainless steel, nylon, Teflon. Of the stainless steel, we can only use stainless steel 304, which is a particular type of stainless steel. And then there are requirements about material interfaces. That is, because of the danger of leaving behind any amount of radioactivity inside of the detector that would be caused by, say, a part flaking off, you are not allowed to have metal-on-metal interfaces. You're not allowed to have a lot of different things that would make life a lot easier. You also have extreme radio purity requirements. Everything that you do has to be extremely radio pure, because any radioactivity that you introduce into the detector is a background signal that has to be calibrated out later. So we have requirements about that. We have intense material cleanliness requirements. Everything that we build for the detector was done in an ISO 7 clean room, after being electropolished, after being washed in a couple of different chemical rinses to try and make sure that the absolute minimum of dust and other contaminants will be introduced into the detector. We also have requirements about accuracy and precision. Because of the structure of our detector, the walls between the various compartments are very thin. So if you're not precisely sure where you are, not only does that introduce errors into your data, but also if you bump into anything, you have extreme problems. You're talking about a couple of millimeters of acrylic that, if damaged, will completely ruin the experiment. So you have to know where you are, but you can't introduce sensors or detectors down in there because of material compatibility requirements. Furthermore, you have to keep in mind light-gas tightness, because we have this detector that's extremely sensitive to light and must be kept under a nitrogen blanket. If you introduce light or reactive gases into the detector, it causes problems. It can potentially cause scintillator degradation. This is all bad. So you have to build a very capable and sensitive device. So this is initially what we came up with. So you can see the structure here. It's made entirely out of Lexan with these cords that would be encased in these sort of scrunchy tubes that would be made out of nylon. So this was a prototype that we built. This prototype proved unsatisfactory, and at the end of 5 years of work, following a theory of projects, we arrived at a design that was very different. And the sort of heart of my talk is this idea of the theory of projects, that not only is it enough to know your constraints, but being able to follow this sort of a path allows you to improve on them and know where you're going. So, to begin with, we had to test this device. We had to test it to make sure that it met all of our requirements. So you can see here, this is our testing inside of a mock-up of the chimney to make sure that we don't touch anything. You can see that the structure that we arrived at is very different than the initial structure. We have these stainless steel components with Delrin bearings. If you'll notice in the center here, this is a movie of us moving at an extremely slow speed. You can barely notice that that articulated arm is moving, but it's moving at about 1 millimeter per second against the background. Furthermore, once we had finally produced this arm, we had to validate it. So we had to perform validation tests inside of a clean bag environment. Because the arm itself is over 7 meters long, you have restrictions about what you're able to do, and we like to test the whole length, so we had to build a clean bag that was effectively 7 meters long. In addition to being able to perform these tests, you have to understand what the tests are telling you. So a lot of analysis was performed. So samples of these are, this is one of the reasons why we rejected the initial design, is because there was a droop in the arm. If you read this as going along the arm, how far down does it bend? Under normal conditions, we were seeing with the initial design 4 centimeters of deviation from the top of the, sort of the elbow of the forearm to the tip of the forearm. This was completely unacceptable. We're trying to shoot for centimeter precision, and that's one of the reasons why we had to scrap our initial design. This is showing our precision. This is measuring over the length of motion with the laser ranger. The line represents perfectly linear motion. The data points with the error bars that you can't see because of the size represent our ability to hit the targets that we need to hit. Furthermore, we built extensive simulation environments to try and make sure that we understood what the signals from this articulated arm would look like. So this is an implementation of the articulated arm in the modern configuration in a software simulation package called Jean-4. We built the thing. This is us constructing this at the clean room at Argonne National Lab. You can see the components that are electropolished and how shiny they are. And the shininess does not only make it look pretty, it also means that we're free of surface contaminants. So unless you see that sort of a shininess, there's stainless steel tends to pick up material on the surface, and you have to electropolish it to get rid of that material that's on the surface. So this is our final product that we are currently waiting to get the approval from the technical board to ship out. It's this incredibly powerful calibration device. Here's it moving, or a static picture of it in the z-axis. This is it inside of the clean room after it's been built, and this is during the final testing. We got mineral oil and we tried articulating it in a mirror detector environment, or a detector-like environment, to make sure that we completely understood how this thing moves and that we were confident in our ability to be able to deploy this device safely and successfully. So towards the future, the articulated arm is now ready to deploy. It's a leap forward in the ability to calibrate neutrino experiments like this. It's accurate to within 1 centimeter cubed, precise to within 3 millimeters cubed. It's got safe, smooth motion over the entirety of it. You can see it moving. This is 30 times as fast as we're going to be planning on doing deployments inside of the detector. You can see how nice and smooth that motion is without my wobbly camera. It's an important part of the future of double show, and it's a really powerful device that was able to be built thanks to cooperation between Drexel University, Argonne National Lab, and also the double show experiment team. I'd like to thank people from Argonne National Lab, specifically Frank Skerritt, Victor Guarino, and Ken Wood for their engineering assistance on the double show collaboration. I'd like to thank Michelangelo D'Agostino, Jürgen Reichenbacher, Stefano Parasso, Zelimir Djuric at University of Hawaii, which is where my advisor is right now. I'd like to thank Rishi Mai Handan, Bernd Reinhold, and others, including but not limited to my advisor. Thank you all very much.
A lot to take in.
Yeah, no, I'm sorry. I probably went a little bit too fast, but there's a lot of material that's in this.
What was the biggest technical challenge, you say?
The biggest technical challenge was being able to successfully articulate, because when our articulation system is driven by a piston, so this piston pushes out and it pulls up a cable which is attached to the near